chapter 11 and maybe take a little sneak peek into 12.
It's got kind of a weird perspective, but it's like
only use that one.
Yeah, pretty much. Yeah, I can't really do much with that. I have to suspend it from the ceiling. So, section 11.9 is a little strange at first. I mean, it's kind of hard to get what they're trying to make a point out of. So I want to start with something we can definitely get a hold of. And it's the example they have in here. Somebody tell me, what shape does that describe? It would actually plot out all the points these vectors are pointing to. Yeah. So just make a circle, right? And the nice thing is, this is in 2 dimensions, right? I don't know if anybody remembers that discussion we had with the 2-dimensional thing where you get the slope to pop out. Isn't the slope basically y over x? So in this case, wouldn't the slope be tangent, right? Which is why we call tangent lines what we do. I mean, that's the connection there. I'm sure some of your teachers somewhere told you tangent is related to slope very intimately, and you can see that here, the slope of that circle. How long does it take to make the whole circle out? Is that far enough? Did I go far enough on the interval that I gave it? Does it make the complete circle? Yes. Cool. So if I have this, get in there. Let me make it a little different than the book. And I give it the same interval. Does that still describe a circle? Okay.
it's like half a circle.
Because when you plug in 2 pi, what do you actually take the cosine of? Pi. So you've only gone up to pi in that case, right? So when you plug in like pi, that's really just pi over 2. So this is just going to make half a circle. So really the idea is, as I step my t along, as I change my t, every change in t is exactly equal to the change in arc length. And that's why radians are defined the way they are. Radians are the real measure, right? What do radians measure?
Arc length.
Arc length. Cool. So that's really, t is in radians. Radians are measures of arc length. So as t goes from 0 to 1, so does the arc length go from 0 to 1. Is that the same thing? Can I say the same thing about this one? Can I? No. Well, let's look at this a little more directly. Can somebody help me out? How do I get the arc length of this number 1 here? How do I get the arc length? And let's do this. Let's do the integral from 0 to t, just to do that. So any t I want to in the middle, right? 0 to t cosine. How would I do that? And actually, what would it be? Yeah, so this would be negative sine squared. Let me just write it. Plus cosine squared dt. Right. And of course, the nice thing is sine squared plus cosine squared is square root of 1 is 1. So I get 1 evaluated from 0 to t. Well, the interval of 1, which is t. And forget about me using the same letter. What do I get there? When you plug a t in for t, you get t. When you plug a 0 in, you get 0. I love it. So what does this really mean? Every step of t, every step I take on this of just t is a corresponding step of t on the arc length. They correspond directly. So it's kind of nice. Every step, every change on my input is exactly the same amount of output. They go along with each other. So the arc length is the same thing as my parameter. They're really the same thing. So that's why the first part of this is called arc length as parameter. So what they say is this is kind of a strange situation. You don't always get something nice like this. How do I mess with a given function to make it work that way? So in this other one, that doesn't work that way. What do I get when I get? You guys do this arc length up to some arbitrary t. So do it for that guy. Finish that one out. So square root. What's the derivative of cosine of 1/2 t? I like it. That 1/2 pops out with the chain rule, right? Squared plus 1/2 cosine 1/2 t squared dt. So here I get square root of 1/4 sine squared something plus 1/4 cosine squared, same thing, right? Since I have the same coefficient, I can pull that out. So I get a square root of 1/4 sine squared is something plus cosine squared is something. Don't let the inside bother you. All it has to do is be the same, and then the identity kicks in. It can be sine squared of w x square root of w, as long as it's both that. The sine squared and cosine squared equals 1. Yeah, 1/2 t. Right? Plug a t in, you get t. We plug a 0 in, you get 0. So every time I change t, how much do I actually move around the arc length? How much do I actually change the arc length? Half a t. That's why this only goes halfway for the same amount of inputs, right? Because I give it a bigger t, I only take a half a step up. Like shit, I mean, it's going to take me twice as long, of course, to really circle this thing out. The example they give in the book has a 2 there, so they would have the opposite problem. They would like go around the thing twice. So who has a suggestion then? Realizing that t is a dummy variable that it can replace with anything, just like a u sub idea, really.
Divide everything by 2 in the thing, and then kind of like it's t half, like half of t goes from 0 to pi. That makes sense?
You're kind of on the right track. How do I force this thing to come out to be just t? What do I really want to do with this integral? I want to multiply it by 2. Right? So what I can do is to really force this thing to work, I can replace, I can replace 1/2 t. I can replace that, no, I'm sorry. I can replace t. What do you think I could plug in there now? Since I got up to half t, I'm going to replace t with twice something. And we're not going to make it the same letter. We're going to say twice s. And the reason we use s is because s is very often thought of as arc length. You guys have seen this in the formula, what's r times theta? You have an r times a theta. Isn't that s the arc length? That's why they use s, of course, thank God, because it is the arc length. We've already established that. So as I say, replace t with 2s. So if you plug that in there, you're going to get really this. Cosine s, sine s, right? Okay, we're doing okay. So just to kind of make this into a little procedure here. Let me see where I got this. No, still working. Oh yeah. Blah, 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 blah. Oh, so if you do this integral of some given thing, let me see, let me make this up. So if I have some r, and I take the integral, now what's v here? What's that v, of course? Yeah, it's r prime, right? It's like a velocity. So this is really just r prime like we did there, right? If I take, and of course this is the magnitude, and that's why the equation is square root of the component squared. That's how you get the magnitude of any vector. So it's just really what we did there. And this comes out to be LT. Then you can set t equal to 1 over LS. And that's going to force it, of course, to have the integral come out to be 1t. Right? And then that means that the dt, the change in your input, the change in your parameter, is equal to the change in the arc length. And it doesn't have to be a circle in this case. It could be anything. Circle is just a specific example I gave. It could be any curve. As you go around some twisty road, go up the one, up the coast, you can figure out what's going to happen. Yeah?
So will the period change? So it will be 0 S to L? I mean, like, well, if you write from 0 like to 2 pi, then it will be 0 to L.
Well, now you've defined kind of, it's the same thing as it used to be. Now it's just a function of S. So when you go to find the arc length, it would be 0 to whatever S ds, because now that's your variable. But the letter I use in the function doesn't matter. We all know that now. It's just a dummy variable. I can make it whatever I want to. So making this direct t is 1 over ls doesn't really change anything, truly. I still get all the same outputs, just for different inputs. Right? That's really what happens when we replace a variable with something other expression. Okay. The nice thing is, if you didn't quite get this, we're not going to focus on this a lot. I really just needed to lay the groundwork so we can build better equations that have nothing to do with any of this shit, thankfully. I just have to be able to refer to this kind of idea as we make these better equations. What we're working towards is to somehow define something analogous to what we did in calculus, which is we've taken higher derivatives of stuff so far, but what did those higher derivatives used to mean? So when I took the first derivative, that was slope. The second derivative was slope of the slope, which is also called the concavity. Cool. And we often call that the way it curved. Did it curve, cup up, cup down? How did it curve? So here we're trying to come up with some kind of generalized curvature idea. And it's a little weird about cup up and cup down, because this thing can do this, and then it can go like that, and then it can go like this, and then it can, there's no up and down anymore, really. It's freaking up in space. Who knows where the hell you're looking. Okay. So here's the idea with curvature. First thing we had to do is figure out what this S is. So S is the true arc length as parameter. So that's what that S represents. So S is the arc length. So we already know one little thing that's going to help us out. We already know how to get the unit tangent vector, for example. Somebody remind me, how do you get the unit tangent vector for some given R? Yeah, T equals
R prime T over the magnitude.
I love it. So we know this here. All right. And it only makes sense. R prime, of course, is a tangent vector. And to make it a unit vector, we just divide by its length. Right? R prime, we know, is the slope, in a way. Right? What's tangent to it. So what I have to do here is I have to directly work with this tangent vector. Considering how poorly I draw, look on the top of page 761. This makes it a little easier. I'm going to try to draw something like that top one, I think. That first one. Okay, so that's roughly what that looks like. It's not too terrible. Where is, now what do you think, what's your gut? I already kind of answered this question. The t is based on the first derivative. It's not directly, because we're talking about vectors. Not everything's going to be perfect, the analogies we make. But the t is like the first derivative, which is why it basically is the slope in a way, at a point, roughly. You guys kind of with me so far? I know, that sounds great. It would be, so the t in this case right there, the t would be just like what we'd expect it to be. It's tangent to the curve at that point, right? And refer to the picture in the book. It might be a little easier to follow in there too. Now to try to cut to the chase on this one, what do you think I'm going to do with that t to then go to the next level and try to get something about the curvature of this thing, which should be like the concavity was in 2 dimensions? Take the derivative again. Now if I just directly do dt, where would that be up here? And actually, let me first do ds, and then we'll bring dt into it. So here's this is what I'm going to kind of do what they did in the book. So here's the delta S right there, right? From here to there. That's how much the arc changed, right? Here's your, let me use the same things they got. Yeah, okay. So here's T of S, and here's T of S plus delta S. Cool. So here's a nice physical example. I want this curvature to be independent of how quickly something's moving around this. Think of it as like a track, let's stick with the road. So we're going up the one, and there's a piece of the one that's like this. Sometimes it's like that, if you ever drawn the one, pieces of it crumble. But it's like this. Am I going to think that curve is really tight, like that curve is really a strong curve, if I'm going really slow?
No.
Right? I mean, if I'm going really slow, even one that was like this, I would say that wasn't too bad. Oh, this is fine. Whereas if I'm going like a lot of people do, if I had a curve like this, would you say that's a very strong curve? No. Not really. Not related to the one I just had up there, right? But if I'm going fast as hell, isn't that one where my tires might start coming off if I'm not really careful? Right? If I'm going around this curve at 130 miles an hour, I think I'm going to think that curve is pretty tight. Shouldn't the curvature be independent of how fast I'm going around it? You'd look at a racetrack and say what the curvature is. You wouldn't need to put somebody on there and say, pick a speed. Okay, now the curvature is this. It shouldn't be dependent on how quickly you go around that path. Are you guys kind of with me here? So somehow I have to just take out the influence that the velocity has. Okay. So what we'll do is, and I want to kind of try to get away from a lot of what they do here. They work this out and they figure out the dt dt. And really, to cut to the chase, well, like we just said, I have to kill the influence the velocity has. So I have to divide by the magnitude of the velocity. I have to take that out. So if someone's going around really, really fast, I'm going to divide by their magnitude of that, and that's going to cancel it out. Compared to somebody going really, really slow, I'm going to divide by a very small number and pick the curvature back up to where it's supposed to be. How are we doing so far? A little decent, okay. So let me kind of go through it more mathematically. Now I've got kind of a visual of a physical situation. So we start with dt ds. And the little symbol for curvature is a little kappa. All right, so it's got a little symbol for itself. A little kappa dude. It's the curvature of something. So the curvature is this dTTS. It's exactly how much the tangent vector is changing as I go around the curve. If I want to take it down to this, so I don't have to do all that weirdness we did earlier to figure out what S should be. You guys kind of with me here? I don't want to have to figure out what S is. I want to do it based on just T. It's easy. Give me an RT, I can take the derivative with respect to T. No problem. So let me base everything on T. The problem what we get when we do that is, now it depends on how quickly you're going around that sucker. So I need to kill that V. So one little thing I put on the side here is, what's somebody's velocity as they're going around this track? What is somebody's velocity as they're going around this track? So here's the arc length, how it's changing, right? What's happening kind of in the background of this for some R of t? I just really want you guys with me on this. This is a little weird. So just like we were doing earlier, actually, let's go with the circles. The one that got all the way through the circle, was it going faster or slower than the one that got only halfway through the circle? It was, of course, going faster. So as I'm changing my t, I'm covering more ground. Right? So my velocity here is going to be how much ground I cover divided by how many steps I took. So if I'm walking, how many steps I took, I'm not going to cover much ground. But if I'm running, the same amount of steps, I'm covering a lot more ground. So it's going to be this. Which boils down to ds dt. When you stop taking gross steps, you take little tiny infinitesimal steps, right? So right here, this is kind of cool. What's ds equal to then? If v equals ds over dt, what's ds equal to? V times dt. So really all we did here was we took ds and replaced it with v dt. Because that's what the hell it is, right? How fast I'm going times the number of steps I took is how far I went. Not a major breakthrough, right? Okay, so a lot of times you can get to the answer a little bit quicker by just reasoning out what the hell's going on. So what have we got then? We've got this nice way of calculating curvature. Believe it or not, did I put that? Yeah. So that's the curvature for some curve. So let's do the curvature for a circle. And actually, let's do one for like, doing okay?
Yeah. Cool.
Yeah, here we go, cool. Okay. So that's certainly a circle. Of radius what? I like it, cool. Because, 5 is as far as either one of these goes out. So when t is 0, it's on the x-axis way here, 5. When t is pi over 2, it's 5 on the y. So it's 5, radius of 5 all the way around. Cool, I love it. Okay. So let's apply it. What's the curvature of this then? At any point. You want to break this down into the parts you have to do. Do you see how just to get to here, I got to freaking do t first? So there's a few steps involved. So I got to first figure out what t is. And we know how to get t. How do we get t?
Derivative of magnitude.
By the way, I'm not being terribly careful here with my little vectors, but following the book is bold in the book. They have an easier job of it. So t is going to be that r prime divided by the length of r prime. So you start to see how to attack this kind of problem. Let's say find the curvature at any point on this given r. You have to first calculate what the unit tangent vector is. Take the derivative of that, divided by the velocity again, right?
Isn't it the velocity is r prime t? So we can just make it.
You gotta be careful though, there's that little intermediate step about taking the derivative of this before you divide by the velocity again. So you can't really divide by the velocity squared, the magnitude squared.
Yeah.
There's that intermediate step taking the derivative. Alright, so what do you get here? This is not too bad. And the length of that, of course, would be, yeah, we just figured that out, so that's going to be 5. So cool. Square root of 25, sine squared, 25 cosine squared, comes out to 1, and square root of 25 is 5. So then you just get, which you sort of should expect. I mean, that's definitely a unit vector. That's the whole idea of the unit circle, right? You learned a unit circle before you knew what the hell a unit vector is, but now that's right off the unit circle. So it's definitely a unit vector. Then I take the derivative of that, get its magnitude, right? So what's the derivative of that?
80%
I like it. And then the magnitude of that, just 1, I love it. And then the last step is to take that, yes ma'am.
No, I don't think I have.
So here's t, is that cool? T,
Okay, yeah.
then take the derivative of this, that's there.
Okay, all right.
Then the magnitude, that's there. So we're building what this thing wants from me, right?
Magnitude.
Yeah, magnitude of dt. So here's the derivative of this,
Yeah.
this here.
Mm-hmm.
The magnitude of this, which would be the magnitude of dt, is 1. And then what's the next step?
Divided by Okay.
1 over the magnitude of the velocity. Well, the magnitude of the velocity is 5. So the nice thing is you've already done that work. You just bring it back from there. 1/5. So what's true then about any circle? It didn't matter what number I put in there. Just change the radius. Any circle has what kind of curvature?
1 over.
1 over the r, but more generally, does that curvature change as I move around the circle? No, and it makes sense. That's why it's a circle, right? What kind of thing would have a curvature that's not constant, that's not too far from a circle? An ellipse. And when you move around that bad boy, the curvature changes, right? It gets a little flatter and the broad ends and a little more curved on the ends, right? Okay. So let me give you one more to try that's not just a circle. Say again?
Where did the B come from?
Here, right? And that was from the whole thing about ds is equal to v dt.
And how did you calculate for that?
Oh, we already kind of did it here. That's the awesome thing. There's so many steps, but thank God in one step you do something that you need later anyway. Yeah, there's your magnitude of v.
So magnitude of v is the magnitude of the derivative.
Beautiful, because the derivative of r is the velocity. Cool. I like it. Cool. All right. So if you really wanted to, anywhere you see a v, you can just put r prime if it's, r prime of t if you want to. That's really all it is. Good. Let's do. What do you think about a line? Of course, a line should have. What kind of curvature should a line have? 0 curvature. Yeah. Cool. Let's do. No, that's not interesting. Let's do this. What's the curvature of this ellipse? What do you think is going to happen? Well, I'll let you guys try this out. It's really funny. It's not very far from a circle, but you know this already that they get pretty ugly because you can't use your cosine squared, sine squared as much as you want to. I want to make you guys do this on your own. Catch up to you a little bit. So obviously that's already disgusting, right? You could, if you wanted to, you could take 4 cosine squares plus 4 sine squares, and that's leaving you with how many other sine squares?
5.
5. Okay, cool. All right, so if you wanted to, you can make this. Uh, 4 cosine squared, 4 sine squared would be just 4, and you got your 5 sine squared. I'm not going to make you keep going with this. You can see how ugly. One reason I want to do this is because people don't realize ellipses, even though they're almost circles, they're very close to being circles, the math gets disgusting as hell very quickly. Just because of that one fact. They don't have the same coefficient, so I can't put them together as easy as I could before. So to keep going with this, you'd have to take dt, right? And that gets pretty ugly pretty quick. I mean, you can just bang that out. I mean, derivatives are easy in the fact that you can always do them. They're not always quick. They're always easy. But this would be a couple of quotient rules, right? Then you the magnitude of that thing. I mean, that gets pretty disgusting quickly. So let me give you one that's not so ugly. I'll let you do it all the way out. Let's do. So find the curvature for that. So what are you guys noticing? Very quickly. Yeah, it's basically the same problem there, right? So I'm hoping you guys realize I'm not just being evil. I'm building up to another method for this thing that's easier when you have almost anything other than a circle, really. You end up with these square roots for that magnitude, and you really normally can't do much with them, which makes your derivatives that much more disgusting. So we need some other method for calculating kappa. And I'm not sure how much, well, let me just cut to the chase on this because we're not going to use this too much, but if you needed the curvature, you could just do this here. Which, believe it or not, very often is a lot easier.
Wow.
And that's obvious. No. I mean, they run through the derivation on the bottom of page 762. I'm really not going to use this formula that much. But I think I gave you 1 or 2 problems in the homework that uses this.
Yeah.
Okay, so what's A, what's B?
You guys help me out. For this guy here,
Oh, acceleration.
V is going to be what? We already kind of did it earlier.
1,
Yeah.
yeah, 6T, 0.
Okay. And what's A going to be?
0,
0,
6,
6,
0.
0.
All right, so what's V, A cross V, sorry. So you got your I, J, K, you got your 1, 6T, 0, and you got your 0, 6, 0, right? Actually, you just need the magnitude, but,
You get 0, 6, 0. I take the other derivative.
hmm?
You take the other derivative, you get 0, 6, 0.
Yeah, velocity is the first derivative,
Oh,
acceleration is the second
acceleration.
derivative. Yeah,
Okay.
cool.
6K.
So what do you guys get for this? We get
6K.
Yeah, we just get 6K. Because everything else, 0, 0, 0, 0. Which K's got nothing but 0 in there. And then, so what's the magnitude of A cross V? 6, cool, right? Because how long would 6K be? Well, it's 6. It's on that one axis. I can just count it. So I just got to divide that by the magnitude of V cubed, and I'm done. That's a lot better. I mean, that, you can see the derivation in the book. I'm not going to step through it again. But it really bypasses a lot of the middle steps that we saw up here with the square roots and all kind of. It really gets right down to what matters most. I don't need all the intermediate steps. So to get the kappa here, it's 6 divided by magnitude of V. What would that be?
1 plus 36T.
Yes, the square root of 1 plus 36t squared. So it'll be, and you saw that if you were doing the work, you saw a bunch of 1 plus 36t squared to the 3 halves kind of things happening. So sure enough, you divide by the cube of this, and you get 1 plus 36t squared to the 3 halves. It really cuts through a lot of the unnecessary component and then putting them all back together. Puts it all back together for us right from the get-go. Okay. So you can see, I mean, most equations we run into are probably going to have the same problems that because the radicals are going to be ugly when you do the magnitude. It's going to be ugly. Okay. Oh, let's see. Oh, cool. Okay, So the last little piece of this is we've got this idea of the tangent vector, the unit tangent vector. The thing we're missing is a unit normal vector. And what's the word normal? It's come up a couple times in the book. Don't you love it?
Yeah.
So perpendicular is orthogonal is normal. It must be really important if we give it so many freaking names. Right? If you do physics, and I remember about half you guys have done physics, you talk about normal force all the time. It's the force a book is exerting on the table because the normal to the plane of the table is this vector. That's the normal force. Right? It's keeping the book up, so it must be pointing away from the table, away from the surface of the table. And this guy is kind of nifty. Let me see if I can make this make some sense. Here goes with another picture. Okay. So here's my, we'll move it along. Here's dt Now we've done this, but what is this really? Where is this on the graph? This is where it gets interesting. So here's t. Here's t. Who remembers if I take t plus that, I have to end up at the next step up, right? If I take a step of that, I should end up at the next, I should kind of get to where I'm going. So really what's happening here is, let me see if I can make this a little bit better. If I'm turning in like this, here's my t. How, and then the next step, it should be a little bit more that way. So how, isn't it a difference here? Isn't that the vector I've added to make it point in the right direction now? So let me maybe it's more pronounced. Here's my tangent vector right now. If I go up and point up here, now my tangent vector is here. Hasn't it changed by that much? Right? So in fact, if you keep stepping it in and in, like we did way back in calculus to get what it is right at this point, it's always going to be perpendicular, and that's why we call it the normal vector. Of course, it's going to be perpendicular to the tangent vector. Right? So it's always got to be true is t, the tangent vector, dot with the normal vector has got to be 0. They've got to be 90-degree angles, and that's why we call it a normal vector, an orthogonal vector. So to get this thing, like we just saw, this dt is kind of like pointing in the right direction, but I want it to be a unit normal vector. So if the dt is pointing in the right direction, how do I make it the unit vector that I want? Divided by the magnitude, exactly. Cool. Amazing, right? Okay, so that's how I can get the normal vector. Now, the whole reason we want this idea is because I want to be able to break vectors down into something. We did this on the, I think I had something like this on the practice test. Make it orthogonal to something and make it parallel to that same thing, right? So I can break it down into components based on any vector I want. So if you really want to set up your own coordinate system, you have set vectors, and you might want to lay one axis on a vector, and then you want to see what's the other vector then in terms of that. Well, you have to see what the components are. So that's why I want to be able to calculate a normal vector. So they do a specific thing with acceleration here. Let me see if I want to do this. Yeah, cool. Let's see if I can get this to crux. So if I have an acceleration, so here's my RT. And so like right here, maybe it's accelerating in this direction here. Okay. And again, they have better pictures. Like on the bottom, page 766. A little bit better there, maybe. I want to be able to figure out what are the components of acceleration that are in the direction that I'm moving, and what's the component normal to the direction I'm moving. So this would be a tangential, and this would be a normal, incredibly enough. All right. So then I'd have sort of like my acceleration vector would then be the normal piece in the normal direction, plus the tangential piece in the tangential direction. That's nothing major there, hopefully. Okay. So all we need are, how do I get this and how do I get that? And what's funny to me is I've already made you do this kind of thing. You've already gone through the math once without any help from me directly if you did that practice test or just looked at the answer key at least. Here's the ugly answer. All right? And now I have these things memorized. Oh, yeah. The normal is going to be, not surprisingly maybe, based on the cross product. Right? And that looks a lot like that shortcut we just had a minute ago, A cross V over V cubed. That's the normal. And the tangential then should probably be based on the, what kind of tells me in the same direction. Cross is kind of like orthogonal to it. Dot product, yeah. So it's kind of, the beautiful thing is, it's just that. Wow. So we have a way to find n. We have a way to find t. We have those formulas. We have, this is what I called, and you guys should have picked up on this, this is what I call the ugly way to find these. It's not really terribly ugly, but it's a lot uglier than it has to be. If I have to find this anyway, and I have to find this anyway, so for example, if I have a vector here, and here's the, I want to break it down into, like, here's the tangential, here's the normal. I want to find the components of that. With these, isn't there a much quicker way to do that? If I have a vector and I have to find these stupid things anyway, don't I? I have to put that one there and that one there, I have to find them anyway. Why would I go through this ugly stuff when I can really just take, let me put A here so it's a little more long with what I'm saying there. A, how do I get the piece that goes along n? Considering n, what's the length of n? And I know I've told a lot to you today, but what's the length of n? N and t are both what kind of vectors?
Unit.
So the length of n is 1. So I really just need a dot n. So the quick way, the nice way, is an is a dot freaking n. So what's at? A dot freaking t. Cool. So personally, I wanted to show you that so you can kind of see why it makes sense one's a cross and one's a dot, why it might make sense.
And they're both done.
But this is more direct.
Yeah.
This one is just saying, I already know what A is. I have to calculate n and t anyway. So why not just find the component of it on this and the component of it on that? That's just dot products. That's all it is. And they do kind of say in the book, they kind of, after all this stuff about this, on page 767, they finally just say, one way is to compute the normal and tangential components directly using the definitions. More efficient is to do it this way. Yes, let's just do it that way. That'd be much better. So let me give you an example so we can actually see concrete thing working. Hopefully give you one. Let's make it semi-nice. All right, that'll be fine. I think that's the right. Here we go. Yeah. Yeah, just, you know. We'll do this together. And it says find the tangential and normal pieces of the acceleration. So of course, who's got a good first step besides turn and scream and run? Why? What's really the first thing I want to get?
You want to get acceleration.
Okay, first off I want to get the acceleration. So the velocity would be, let's just go through real quick. Negative sine, 6 cosine, square root of 5, negative. Is that cool?
Yep.
And then the acceleration again would just be another. So don't worry about the square root of 5. They put it in there to actually make this work come out nice, believe it or not. Be careful with the coefficients, they can make the work come out nice. What do I want to do next? Beautiful. Find these unit tangent and unit normal vector. I love it. So the unit tangent vector, as always, is r prime over the length of r prime. Or v over the length of v, whatever way you want to look at it. So here's v. Now the length of v, we might think, oh God, I don't even want to do it. Let me just skip that one, hope you didn't see. But they should have made, I don't know if they did, but they should have made this the coefficients nice. And I'm pretty sure they did, right? Because you only have a 1 plus a 5 is 6. It sounds like they did a good job. The length would be sine squared, right? Plus 36 cosine squared plus 5 sine squared. Well, they didn't do such a great job. I don't know. Did I lose something? No. If only they would have square rooted on the 6, that would have actually worked out, wouldn't it? Right? No, if you combine the signs, you get your 6. I think they were trying to make it work. What did they forget? They should have put a square root of 6, right? Let's do that, right? Yeah, let's check. They meant to do this, didn't they?
Yeah.
That's what I like to hear.
We did it on the test. I think you meant to do it.
Yeah. I like that. No, I'm the teacher. I get to do this. You can't say. I think you meant this question. I like that. It's very So what are you going to get? So this is just a unit tangent vector. What do you get on the bottom, by the way? Let's see. 6. You just get 6, right?
Yeah.
Well, square root of 6 anyway. Right, 6 sine, 6 cosine, so you get square root of 6 times 1, so you get square root of 6. And then on the top you still get this here. Which is nice. Right, those would cancel out. So there's a unit tangent vector. What's the unit normal vector? Who remembers through all the stuff that I've told you today how to get this guy? Yeah, we had this, right? Now remember the cross product thing was for the a cross v over v cubed, was for the curvature, not the normal, yeah. Yeah, so now I just got to take the derivative of that thing. All right, so the square root of 6 is just going to come for the ride. And I've already done the derivative. That's really just the, let me see. Yeah, since this isn't really dependent on t, as you do this, you'll pick out stuff like this. This is not dependent on t. I've already done this guy's derivative. That just comes for the ride. So basically, I already done the work. Just got to put it over square root of 6. You guys kind of with me here? When that's a function of t, obviously everything changes, so I've got to do a fresh derivative. It's not a function of t. I've already done the derivative. So it's negative cosine square root of 6, negative sine, the square root of 6 is canceled, and then negative root 5 over 6 cosine over the length of that. This might get kind of ugly here. Very roughly, let's see. We'll get 1/6 cosine squared plus sine squared. Yeah, this comes out nice. So I'm pretty sure that's what they meant. That.
It's just a typo in the book.
Just to remind you guys, you can't say that for me. Whoops, not that. Length of that. That's nice. 6. So you just get 1 on the bottom, right? So here's the answer for that. Oops, kind of over there, aren't I? Thanks, man. And now you just do the dot products and you'll be done. So we've got our acceleration. If you dot it with n, you'll get the an. If you dot it with t, you'll get the at. So everything we did here doesn't matter which way you do. You got to find n, you got to find t, or whatever. But now I've got a way to do the an quicker. So it'd be a dotted with n, which is right here. Oops, it's just a negative sign. Okay, so then I'll get, see, negatives cancel. I get 1 over root 6 cosine squared, right? Bam, bam. plus the 9 minus cancels, square root of 6 sine squared, plus I think it's the square root here, right? Yeah. 5 over square root of 6 cosine squared. Oops. Which will get 6 over root 6 when you put your like terms together. That's your AN. Then you can get AT in much the same way. Just take A dotted with, A dotted with T, which I think I've taken away. Here's T. So A dotted with T. Cool, same way. Right. The bigger thing I want you to get from this is, if you can find orthogonal vectors. I keep saying this thing, and I've said this before, unit vectors are awesome because you can build off of them. But a lot of you guys, I think, don't really see how that fits together. How would I write, when we know that this is true, I can write this like this. What this really means is I've got 2 of these unit vectors minus 5 of these unit vectors plus 6 of these unit vectors going together to make this, right? So we see this kind of thing all the time, where if I can make unit vectors, they might be ugly unit vectors because they could be pointing whatever direction, but they're definitely going to be orthogonal to each other. And I can find any vector and see its components on those unit vectors and see what that vector looks like in terms of my, like, I prime, j prime, if I want to, like a k prime, like a new coordinate system. All I have to do is do these dot products. If I can find the normal, the tangential, I can do the dot products to see what that looks like. Right, that's what this is trying to say. Okay, cool. And that's why I didn't do a lot of homework out of section 11.9. Pretty much, yeah. Tell me what to do. Oh. So everybody got this board here? If you want it?
Very bottom.
The very bottom? Okay.
Did you solve for A of N and not AT?
Yeah, I didn't do AT. It's the same way, yeah, sorry. I figured that was enough to go through. Yeah.
That's a plus 6 square root of 6 sine. Right?
Here, yeah.
Yeah, it's plus. Yeah.
So I just want to do a sneak peek at 12.1 real quick. Because it directly relates to one of your homework problems one of the test problems that a lot of people didn't like. And that was that one where it said, find an expression in 2 variables for all the vectors orthogonal to this thing, right? So just to kind of give you a major, or more than a hint. You got that, Ben?
Yeah, good.
Cool. Just give you the way to do that problem, and then I want to show you how that relates to what a plane really is. Because how many variables do I need for a line? How many variables do I need for a line? 1. T. And then some A, B, C, some direction vector, right? That makes sense. Lines are one-dimensional. They should take one thing. So when I asked you to do this problem where it was find all vectors orthogonal to something, let's just make another one up, 7, 8, negative 1. So here's how you do that problem. You start here. A lot of you guys are starting with the 2 variable thing. You're all just focusing so much on that, and you like made the 0 or whatever. No, that's going to come out of your work. Start here. That's what you can actually do. You can force it to be orthogonal. What would you do then? You would take the vector I gave you, dotted with your vector. What's your vector? Sure, ABC or XYZ or whatever the hell. Because you don't know what it is. Just like algebra, you like X. For us, R3, our variable is ABC. Right, vector. And this has got to equal 0 for orthogonal. And what do you get? You get 7A plus AB minus... And a lot of you guys got to a point like this, but then you did all this other work. I'm not sure what you were doing.